Okay, so with this problem, we want to show that if we have an integral domain a multiplicative subset is saturated if and only if its complement is a union of prime ideals. So first, let's recall the definition of what a saturated multiplicative set is. So recall a multiplicative subset of a ring multiplicative subset S of a ring is saturated if given two elements of our ring, their product is in our set implies that both A and B are in our multiplicative set. So for this problem, we're going to prove the reverse direction first. It's a bit easier. So let's assume that the complement of our multiplicative set is a union of prime ideals of A. So we want to show that S must therefore be saturated. So in order to show saturation, we look at our definition and we take, we suppose that AB is in our set S. Okay. If neither A nor B is in S, then they must be in the complement of S. Then A or B in A set minus S. But what would this mean? Since the complement is the union of a bunch of prime ideals, then A or B okay, let's go ahead and say, without loss of generality, assume A is in the complement, then A is contained in some prime ideal P. And since P is an ideal and B is an element of A, then AB is certainly in P as well. But this would mean, well, P is contained in the complement, so that AB is contained in the complement, which is a contradiction. Since we, by assumption, AB is in S here. Therefore, both A and B are in S, because we could run the same argument with B being in P, then AB is in P. We are in an integral domain. It's commutative. Okay, so now for the forward direction. This one is a bit more complicated. We suppose that our multiplicative subset S is saturated. We want to show that for every x in the complement, x is contained in P for some prime ideal P. Let's go ahead and call it P sub x for some prime ideal P sub x, and in addition, P sub x, our prime ideal, is disjoint from S, so that P sub x is completely contained in the complement of S. Right? Okay. So how are we going to do this? We're going to have to use a Zorn's lemma argument. So let's define a set. I'll call it capital Phi. To be all ideals of A such that are disjoint from S. Oops. The intersection with S is empty. Okay. So in order to use Zorn's lemma, we need two conditions. We need to show first phi is non-empty, and two, that, well, okay, phi needs to be a partially ordered set, but with ideals we always have the partial ordering of containment, and so that every chain in our set here, partially ordered set, has an upper bound. Then if we can prove these two conditions are satisfied with phi here, then Zorn's lemma tells us that phi contains a maximal element. Okay, then we're going to use that maximal element and show that it is prime. Okay, but for every x in the complement, and here we do need to assume that A mod S is non-empty. Because if that wasn't the case, then iota would be empty, or sorry, phi here would be empty. But we do, in our multiplicative set, we're going to go ahead and assume that 0 is not in it. Let's go ahead and assume that S is a proper subset of A. We'll just assume that, because otherwise, you know, this argument is trivial. All right. The complement of S would be empty, and the empty set is the empty union of the empty ideal. I don't know if that argument holds water. But anyways, let's go ahead and assume S is a proper multiplicative subset of A. In any case, the ideal generated by X is disjoint from S. This is a claim. I'll need to make a quick argument. So if it wasn't disjoint from S, then there exists an A with A times X in S, right? Because that's what all the elements of this idea look like. If that were the case, since S saturated, both A and X in S, but this contradicts X being in the complement of S. Oops. Which means it can't be an S. All right. So we know that for every element in our complement, the ideal generated by that element is disjoint from S, and therefore this set phi up here, right here, is non-empty. Okay, we satisfied the first condition of Zorn's lemma. So we want to show that every chain has an upper bound. So if we take a chain, ordered by inclusion, let's say we have this set I, let's index it with lambda. And consider, this is typical of a Zorn's lemma argument, the union of all these. Let's call it P. Union over all our lambda. All of these ideals. Okay, well, we need to show that this is, in fact, an ideal. So we need to show that P is contained in capital Phi, so that Phi contains, and that it's an upper bound. So let's take two elements in P, take an A and a B in P, then there exists a mu and an epsilon with A in I mu and B in I epsilon, and either I mu is contained in I epsilon or vice versa. So let's go ahead without loss of generality. Say the above is true. I mu is contained in I epsilon. So that both A and B are in I epsilon, and therefore A plus B is in I epsilon, which is contained in P. Right? Okay, so P is an ideal. Well, okay, we need to actually show. The same applies for the multiplication by any element of A. We can follow a very similar argument. Okay. So P is an ideal, and we want to show that P is disjoint from S. So by a similar argument to this one up here, well, take any x in P, then x is contained in I sub lambda for some lambda. So x not in S by assumption. Therefore, P and S are disjoint. Okay, now Zorn's lemma, we satisfy the two conditions of Zorn's lemma. We can apply it. We get that phi has an upper bound, or has a maximal element by Zorn's lemma. Iota has a maximal element. All right? Okay. So let's call it Q. Okay. Since our phi here contains every ideal generated by an element in the complement of our saturated multiplicative set, for each x in the complement, x is contained in Q for some maximal element of phi, right? Okay. Now we just need to show, we've shown that Q, by assumption, by the definition of phi, since Q is contained in phi, Q is disjoint from S. So we just need to show that Q is prime. Okay. So take the product of two elements in Q. And Q is an ideal. We want to show that either A or B is in Q. Okay. So either Q plus the ideal generated by A is equal to Q, or Q plus the ideal generated by A intersect S is non-empty. The same goes for B. The same argument goes for B. If this is true, then A is contained in Q, and we're done. So let's look at what happens if this were true. So if neither A nor B are in S, then there exists a, let's call it X, X1 in Q with X1 plus Y1A in S, and let's go ahead and say X2, Y1 is in A, Y2 is in A, X2 in Q with x2 plus, oops, this should be y2, y2a, also in S. And since S is multiplicative, their product, x1 plus y1a, oh, this should be B. So I'm assuming, let's assume neither A nor B is in Q. We'll get a contradiction. So it must be that one of them is in Q. X2 plus y2b is in S. And we have, so then this is equal to x1, x2 plus x1, y2b plus x2, y1a plus y1, y2ab. This is in S, but this is in P, or sorry, Q. This is in Q because of this x1. This is in Q because of this x2. And this is in Q because of AB is in Q. Which would imply Q intersect S is non-empty. Contradiction. Therefore, either A or B is in Q. And we have it.